Like he sits in his basement.
You don't know that. You know what? If it's a basement, at least it's a finished basement.
You don't
There
mind.
you go. See? There you go.
Real quick.
Alright, so we're gonna pick up on slide number 17.
You literally just had it. Well, you probably see it.
And you guys very clearly have a good handle on physical versus chemical changes. So now we're gonna move into looking at composition. So what is something made of? Alright, so this is also stuff that is gonna be pretty familiar. So composition of matter is the distribution, the amount, the type of elements that are found within a substance. So, we know that everything is made of atoms, which are made of protons and neutrons and electrons. Those protons, neutrons, and electrons are our subatomic parts, or subatomic particles, right? Because they are sub or smaller, they're below the size of an atom. Those are the things that make up the atom. And so the number of those subatomic particles determine the type of element. Which one of our subatomic particles is the one that actually identifies the element? So if you change this, you're changing the element that you're dealing with. Which one is like that permanent number, or permanent one?
Proton?
The proton, right? Because you can change electrons and you still just have the ion of that element. You can change the number of neutrons and just have the isotope. But if you change, you can't see through me?
No.
You can tell me to move. I just thought it was funny. You keep stretching around it.
I was just trying to like see the.
I know, you're trying to be polite. So changing the number of neutrons gives you an isotope of that element. But if you change protons, that's when you're dealing with a whole new element.
Ethan, Amon, and Katie, Sarah, please.
Okay? All right. So each type, and again, that's kind of nice how this is review. This is what we talked about the very first unit. And here we are already in January, and it's still coming back. So it has not been wasted what you're dealing with, what you've learned, okay? So we know that each type of element has its own unique set of characteristics based on those number of subatomic particles. So that's one way to classify. That's why an oxygen atom is an oxygen atom, is because it has 6 protons. Do you have your notes? The notes that I gave you yesterday? Just came to you yesterday. Are they in your locker? Okay, go grab them. That's fine, just go grab them. All right, I'll mark you down, but definitely get them. All right, so that's one way that we group things is, okay, by how many protons they have, by how many valence electrons they have. Another way of looking at things is when we have a bunch of atoms together to make all of our stuff, all of our substances in the world, what are those things made of, right? How many types of atoms? And there's something called pure substances where it's elements of all the same atoms. So all the oxygens, all the nitrogens, all the berylliums, right? So sometimes these elements will combine where you have nothing but oxygen, nothing but nitrogen. And so we call those obviously our elements, and those are considered to be pure. They're not mixed with anything else. Then we take those elements like hydrogen and oxygen, put them together to make water. That new compound is made of 2 or more elements. They are combined chemically in a fixed ratio or proportion, like 2 hydrogens to every 1 oxygen for H2O or water. And so that is called a compound. Again, this is not new information, but these are what are considered pure substances, where you have all of one type of atom, or you have a compound, right? So NH3 or ammonia, right? That would be one thing, right? So when it combines to make that new compound, it is considered to be pure. It's that one thing. So water, oxygen, water, ammonia, maybe table salt, that sodium chloride, when the sodium and the chlorine come together to make that new compound of salt. The reason that they're considered to be a new thing, even though it's like sodium and chlorine combined, is because it's hard to separate them. They're combined because they are satisfying each other by combining to make that new bond, to make that new compound. All right, and so anytime you're dealing with an element or compounds, they're considered to be pure substances. So I have nothing but table salt in my salt shaker, which would make sense, right? I don't have it combined with anything else, and so that's considered to be a pure substance because it's made of just that one thing. All right, that's a little bit freaky that those were the 3 examples I gave because I haven't even looked at these notes since last year. Whoa, it's like I just knew that's the way my brain works. That's scary. Okay, so pure substances are one category, but then we also know there's a lot of combinations of things, and that's what are called mixtures. Mixtures are where you have more than one thing involved. All right, so it's made of 2 or more substances that can be fairly easily separated. And to separate them, we're using only physical characteristics. So we're not trying to chemically get that sodium away from the chlorine. We could do it, it's just not easy. And that's why that would be considered a pure substance, because you have to chemically separate it. Mixtures can be separated using physical properties. Okay, so like magnetism, size, color, maybe even odor, right? You could separate or group them differently based on those characteristics. So with a mixture, we have 2 different types of those as well. And so we're getting to a lot of our vocab terms today. Homogeneous means the same throughout. So if I'm looking at a gallon of milk, I don't see any difference throughout that gallon, right? I pour it into my glass, I still don't see any difference. So if it looks the same throughout, we call that a homogeneous, or sometimes it'll be pronounced homogeneous mixture. And then we have the other type of mixture, which are the heterogeneous, which means different throughout. So last year, we had these same prefixes of homo and hetero with our homozygous and heterozygous allele pairs, all right? So I know in my class, we talked about it. I know in the world that we're living in, typically when you hear the prefix homo, something pops in your mind, and to say it like as politically correct as I can, if you hear that somebody is in a homosexual relationship, they are in a relationship with someone of the same gender, right? It's the best way to say it. So homo, that prefix, means the same. So that's kind of like probably the go-to example for how we use that prefix in like our daily, everyday life, not like in our science life, but that prefix is used in a lot of different ways. Heterozygous and homozygous, heterogeneous and homogeneous. So we use that last year and this year, and there's other examples as well. But if you remember that the prefix homo means same, then you'll know that you're talking about mixtures that look the same throughout. And if you think about somebody who's in a heterosexual relationship, they are in a relationship with somebody of the opposite gender, right? So, not to get everybody freaked out or like have too much of health class or something going on in here, if you remember those prefixes, it will help you, all right? And I know people get a little giggly, get a little, but they're not doing too bad. Same, different. And what we're talking about, not relationships, mixtures. All right, so a mixture is obviously a combination of 2 or more substances that are not chemically united and do not exist in a fixed proportion to each other. Compounds have to be in that fixed ratio for those elements. So NH3, 1 nitrogen, 3 hydrogen. That's a fixed ratio or proportion. H2O, 2 hydrogen, 1 oxygen. NaCl, 1-to-1 relationship or proportion, right? That makes a pure substance. Mixtures, it's just like random, willy-nilly, it doesn't matter. Like they just are together and then they can get separated with physical characteristics, no problem, all right? And so mixtures are a lot less formal and rigid, like it's more relaxed, like what defines like how to put a mixture together versus how to put a compound together. And so most natural substances are gonna be mixtures. It's just a combination of things that get put together, and then, you should be able to separate them back out physically. If you would take this mixture, eventually you should be able to get it separated out into pure compounds and elements if you would keep breaking it down and breaking it down physically. At some point you get to where you're just left with the elements, and just the compounds themselves, where you can't break them down anymore, without going farther, like to get to like the protons, electrons, and neutrons of those elements. So really, what you need to know, there's pure substances and there's mixtures. With mixtures, you're dealing with either homogeneously mixed or heterogeneously mixed. And then if you do have a mixture, you should be able to use physical properties to separate it out into their individual parts or components. Okay. So, a homogeneous mixture. Here's like a jug of milk. I don't know what that is. Somebody told me one time they think maybe it looks like goat food. I don't know, maybe like weird cereal. But homogeneous means the same. It's going to have the same general composition or appearance throughout. I don't see any difference top to bottom, side to side. Everything looks the same here. I don't see anything different. Worms? Oh, it could. Yeah, it looks a little bit like mealworms. I can see that. Our heterogeneous mixtures obviously are going to look different. They consist of visibly different phases or states of matter, or items. So looking at the taco, tell me something that you see. Now I want tacos. It's Taco Tuesday. What do you see in that taco? Give me something, Kenna.
Tomatoes.
Absolutely. What do you see?
Cheese.
Okay. Gilbert, what do you see? I do too. Billy, what do you see? Okay. Egypt, what do you see? Okay. What do you see?
I'm seeing some sour cream.
Sour cream. I think maybe just what's left is the shell.
The shell's gotta be a part of it.
Well, absolutely. It's holding it all together, right? Good. You just listed like 5 or 6 different things. Different is the key, right? Now, if I put that in a blender and mixed it all up, it's still the same stuff, but then it would be a homogeneous mixture that none of us would really want to eat.
Would it taste the same though?
Ah.
Yeah, it would. I feel like now we gotta.
Possibly, like, but the texture, like the crunchiness of the shell would be gone. So maybe the taste would, I don't know. Maybe, maybe not.
Hey.
I'm just.
I don't know.
I'll run through it after drinking.
Okay, so over here, I get that these are all M&Ms. They have the same chocolate inside. They pretty much do. Does anybody think that the M&Ms, different colors, taste different? You think they do?
Anybody who raises their hand is small brain.
You do realize it's just a thing from your brain, like it automatically makes you
Okay,
think that it's
Skittles do
flavored.
taste different.
Well, the inside of the Skittle, yeah, those are flavored. But the M&Ms are not intentionally.
Skittles are all the
I
same.
saw that, yeah.
Like the
Skittles
colored
says-
goldfish, the red ones taste the best, the red and green ones are way better than like the.
Wait, what is it?
The
Goldfish.
colored goldfish.
Like the crackers?
Yeah.
Yeah.
There's other colors besides orange?
They make,
Yeah.
they make a big thing, it's all different colors, the red ones are the best.
Yeah.
According to
Is
Skittles.
this true?
Yes.
Are they supposed to be, or is it just your brain?
I don't know.
That's just
They're
your
all
brain.
different.
Yeah, no, they say that the different colors makes your brain think that each color has its own flavor.
According to
You know, it's
Skittles.
like watching those brain games. That's what our brain does. Like, it
Especially
tries
like
to
if you read on the back, like the flavor, you'll imagine the flavor when you eat it. The brain's a very powerful thing.
Extremely.
Billy, some guy.
Whoa.
But Skittles in my mind do taste different.
They do. There's-
M&M's don't taste different to me, but like Skittles, they say they're all the same
Yeah.
thing.
Yeah,
Is that
I looked it
true?
up.
Yes, if
Yeah.
you look it up right now,
No,
I'll look it up.
No, stay with me. I'll.
They're all the same flavor,
Okay.
but they taste different.
They do taste
They-
Skittles taste different.
Yeah.
What about Starburst?
Yeah.
Those are, but they're flavored. Like, it actually says like.
Pink's the
I think
best.
those ones are actually flavored, yeah.
Pink's the
But the
best.
Skittles
So it's just
So yeah, I
Skittles.
saw that thing on Skittles that said they're not flavored. It's literally just the
Dang.
same thing with different
You
colors.
guys teach me stuff.
Okay, but like,
Okay.
in my mind, like,
Oh yeah, they
Yeah.
definitely have a
like
different
when they,
taste.
but when you're blindfolded, you cannot tell the difference in any of them.
That's what I'm saying.
But like when you
Same
like
with, like,
see them when you put them in your
chicken
mouth, you can
beverages.
taste.
Have you tried
That's what I'm
that?
saying, that's why I like with the
Have you tried to
M&Ms,
blindfold
because
yourself?
Yes, and it's no different. I ate it.
Tropical one.
My mom gave me.
Okay, we
straight
might have to
from
try
my-
this with Skittles and Starburst.
Starburst.
Starburst are flavored though.
Yeah.
They have to be, there's no way they're not.
So,
If they're
Thanks
not,
to
I'm
Okay.
quitting.
let's go back. That's, you guys just blew my mind. I'm gonna have to look into that. So
Rice Krispies.
honestly, like the M&Ms are not intentionally supposed to be flavored, right? Some people think, yes, they do have a different flavor versus others, or some people are like, oh, I like the green ones, or I like the blue ones, or whatever. Wow, interesting. So, looking at these, can you see physical differences?
Yes.
Color, right? That's pretty much the only, they're the same size, same shape. If you would open them all, like they all look the same inside. So really the only difference, the physical property that we're using is color to point out differences. Besides color, if we got rid of that, like there are stores that are M&M stores, and like they have containers that are all the yellow ones, or all the blue ones, or all the green ones. Then obviously those would be homogeneously mixed because you don't see any difference. But when you have a normal bag or container, right, it's gonna have those differences. Okay. Wow, interesting stuff. So, here's our pure substances, and I believe that you just have to fill in those little white boxes, like at the top, mixture and pure. Right, at the top of that little chart. So, pure substances cannot be broken into something smaller, and still have the same chemical compounds, or same chemical properties. So all of one thing, which we call elements, so silver, gold, oxygen, hydrogen, carbon, or if we have compounds which are chemically bonded, chemically united to make a brand new substance, carbon dioxide, water, magnesium bromide, all of those are not easily separated. They would have to go through a chemical change to separate out, right? So you can have a combination of a few elements to make a compound, or you can just have the elements by themselves. So really, we have obviously much more things that are considered mixtures. So the mixtures are where you have a combination of multiple substances that can't be broken down or easily separated. All right, so within the mixtures, we have two types. We have our homogeneous and we have our heterogeneous. So all solutions are homogeneous. So Kool-Aid, coffee, salt water, the air we breathe, even a plain Hershey bar. Now, notice that Hershey bar is on this side as well, but in parentheses it says with almonds. Because within that Hershey bar, you can clearly see differences. You can see that almond. Or even like the cookies and cream Hershey, right? You can see the cookie part. Okay. Heterogeneous is where you can physically see differences. Pizza. Obviously, you can see the crust, the sauce, the cheese, the toppings. Vegetable soup. You can obviously see all those vegetables floating around in that liquid. So sometimes it's two states together. Solid like the vegetable chunks, and then liquid like the broth. Yes?
Okay, so, I'm kind of confused on the salt water one. Wouldn't that just be regular water too?
It could be, sure. But salt water meaning like if you take salt and dissolve it in water, you can't see that salt anymore. Right? If it's mixed in and dissolved, you can't see the salt. Right? You don't see the chunks of salt floating in it. If you could see the chunks of salt floating, then it would be considered heterogeneous. But if it's dissolved and mixed in, you can't see any difference. Even like the Kool-Aid. If I take the Kool-Aid and I dump it in the water, until I stir it and mix it up, I can see the powder and I can see the liquid. Those are two different things. That would make it heterogeneous. But once it's dissolved and mixed together, it all looks the same. Yeah, no?
I'm just confused with like what the salt water. Like, doesn't the water get cloudy if you mix salt in with the water though?
Yeah, but it's cloudy throughout the whole thing,
Oh.
right? Yeah. Okay. Blood, people are like, wait, I disagree. If you like cut your finger and you have like a little bit of blood or something, it looks the same, right? That would make it homogeneous. If you take that blood, or like if you've ever gotten blood work done, like they pull the blood and they have it in a vial, and if they put it, and we're gonna look at this tomorrow, put it in a centrifuge machine, it will spin it. And as it spins it, it pulls the more dense material to the bottom and the edge. And so your blood is actually made of a lot of different things. It's made of white blood cells, red blood cells, the plasma part. And so it actually layers out into different components. So when it's tested, or if you do something to that, it will kind of settle out into the different components. My bottle here, right? I use this in 8th grade for talking about, like, as you add more speed, different water and wind can carry more sediment, and when there's not very much speed, it can't carry it and it drops the heavier stuff. Well, in this bottle, right now, it kind of looks like chocolate milk. After today, I'll let it sit for a few days and you'll be able to see the bigger stuff is settled at the bottom, and then the water will get more and more clear because the little particles are going to start to settle out too. It just takes them longer because they're more fine and they don't have as much mass, so they're not getting pulled down as quickly or easily. Okay. All right. So looking at this, a plain Hershey bar, homogeneous or heterogeneous? What do you think? Okay. Looks the same throughout. That Snickers bar, hetero. You can clearly see the chocolate, the nougat, the caramel, the peanuts. Pizza, definitely see differences. The Italian salad dressing, and then hot chocolate with no marshmallows. Good. If I put marshmallows, okay. So when I ask you questions, I try to not pick ones where you'd be like, wait a minute, are there marshmallows or not, right? Because that would definitely change your answer. Okay, so if we're talking homogeneous mixtures, we're talking things that look the same throughout, and these are called solutions. So a solution is a homogeneous or homogeneous mixture that is the same uniform appearance throughout. So we're talking like Kool-Aid, we're talking even like chocolate milk. If you add the syrup to the milk and stir it, then it looks the same throughout. If you wait throughout the day like that, chocolate milk that you make yourself will settle out a little bit, right? You get that kind of syrupy layer at the bottom, then it would be heterogeneous.
Would ice water be?
Hetero.
It wouldn't be homogeneous.
Because it's two states of matter. You see the solid and the liquid. Even though chemically it's the same thing, because you see two things, and that's our next point. No, it's a great question, because look, it's comprised of only one phase. So having that ice cube, which is a solid, takes it out of that category. Right? And finally, a suspension is a heterogeneous mixture. So solution is homogeneous, everything's the same throughout. A suspension is heterogeneous, where you can see obvious differences. Usually it's going to be a solid mixed with a liquid. So it could be your ice water situation. It could be like Italian salad dressing, where you have the oil and the vinegar, and then you have the chunks of the vegetables and garlic and stuff. So you have liquid and solid. So this one needs mixed up, obviously. The oil's at the top, so the different densities are kind of settled. But you can see the solids suspended in that vinegar. Something I'm just going to mention, it's not something that we really need to worry too much about, is a colloid, where you have something that's kind of microscopically dispersed, and that's like fog. Right, so fog is actually solid little pieces that moisture has condensed around. Right, so you have a gas and this liquid form kind of all in one. This is also the Golden Gate Bridge, which is a suspension bridge, so I kind of picked that picture because suspended means kind of held within. So it's like these vegetables are held within that liquid. The bridge is suspended by these cables that are holding the actual road part, the actual driving part up, okay? So again, colloid, don't worry too much, it's part of this, but it's not anything too major. But the suspension, where you might have chunks or solids suspended in a liquid, and then you have your solution, which we're gonna look at a lot more, here in the next couple of days, okay? We will start tomorrow with our song, since we didn't get to it today.